Hello everyone. Today in this lecture, we will have a look into the application of synthetic aperture radar. Though it is not a geophysical exploration method, I thought of sharing the application of synthetic aperture radar to you, since this is of greater relevance to civil engineers, mining engineers, as well as geologists, and also to understand major natural disasters. Right? We had a look into the application of ground penetrating radar. Synthetic aperture radar method is also little bit related to the ground penetrating radar. The difference is we are going to use this from space, right? Microwave sensors are the sensors that measures the microwave in this spectrum, right, of electromagnetic spectrum. This particular range is known as microwave. There are sensors deployed in the satellites that can measure the microwaves. The microwave signals can today complement the other optical sensors, right? Other optical sensors are data which we have obtained using optical sensors can be complemented by the microwave sensors too. What are the advantage? Synthetic aperture radar uses microwave as well as radio frequency parts of electromagnetic spectrum, and instrumentation includes radars and radiometers. The greatest advantage is it is immune to clouds, precipitation and smoke. That means when you observe the surface of the earth, the presence of clouds and smoke as well as water is not going to be affecting your records, readings. Right? It also able to penetrate to some extent into the snow, ice, as well as little bit into sand and rocks. And since we are going to generate radar signals, it is not going to rely on the sunlight, unlike the optical sensors. So, optical sensors are able to get the signal only when the sunlight is there, whereas radar signals can be obtained using even during night times. Right? Why do we call this as synthetic aperture radar? Here, since it is going to be mounted in a satellite, it uses a short physical antenna, right? What the antenna does? The antenna generates radar waves, and the radar signal goes and falls on the surface of the earth, and they are backscattered or reflected back, and the reflected back signals are also sensed by a receiver in the same satellite. So, the satellite has both the transmitter as well as the receiver. As the satellite continuously moves along a path, it keeps on transmitting and receiving the signals at different locations along its path. And we use some special software, right? That means electronically we synthesize this data in such a way we have actually deployed a long antenna. In fact, we have not deployed a long antenna, we have put a short antenna. As the satellite moves, right, it gets the data continuously from different locations along a swath path, right, along the flight path. This is the flight path, this is the swath that is covered, right, and the data is synthesized in such a way that we have deployed a long antenna. That is why it is called as synthetic aperture radar, right? Synthetic aperture radar. So, using which we can create image of the subsurface based on the variations in the backscattering of microwaves, right? At a very fine scale of few centimeters is possible, right? What is the advantage? The advantage is today we are able to use this aperture radar to understand the changes that take place on the surface of the earth. Right, here you can see how the land is subsiding by making the measurements of radar signals. That means as the satellite passes today, let us say it is in 1990, right, as it passes and it transmitted the radar signals, it falls on the surface of the earth and gets reflected back. From the arrival time, we know approximately the elevation of this particular spot. Then we repeat, the same satellite may pass over the same area in the year 2000, and in 2000 also we know the elevation. If there is no change, there is no issues. If the land is subsiding, it is able to tell us the land has gone down by so much. That means what we do, we prepare a interferogram using the data obtained at different times. The interferogram help us to understand the regions of land subsidence. So, here is an example where the interferogram is able to identify the locations where there is land subsidence. Right? Land subsidence is usually associated with the withdrawal of large amount of groundwater, especially from confined aquifers. When we withdraw large amount of groundwater, the confining layer at the top, which is usually clay will also lose out some of the water to the lower confined aquifer. As the clay loses water, it will start shrinking, right, leading to land subsidence. So, this can be picked up very nicely using the aperture radar systems, right. What are the other methods of understanding the land subsidence? These are all the traditional methods of understanding the land subsidence. That means you deploy some instrument at the surface of the earth to understand how the land surface is changing, right. The resolution, however, is very good, right, especially vertical resolution. We are measuring the vertical component of displacement, right, in most of the methods. Some of the methods which are horizontal extensometers are often used to understand landslides, mud flows, right, to know how horizontally the land is getting deformed. But they are all point measurements. The advantage of synthetic aperture radar is we are able to map spatially over a large area. See, all of them are point measurements or a measurement made along a line. Especially horizontal extensometers can be helpful to understand how the land is moving along a particular line, whereas synthetic aperture radar help us to map the whole surface as we have seen here, right. In fact, there are ground-based observations. In ground-based observations, we continuously monitor how the water table is changing, as I had indicated in this diagram, how the piezometric surface changes, how does it correspond to the land subsidence can be monitored on the ground. But the advantage of using the satellite based synthetic aperture radar will be very useful, right, since we can map the whole region, right. The radar in the satellite image transmits the signal reaches the surface and gets reflected back, right, and we can, as the satellite moves, we can create a solid image of the subsurface over the swath of this much of distance, right. Since the satellite comes again and again, covers the next swath, the whole world is mapped using the synthetic aperture radar. Then, as I had told you already, during the next trip, maybe after 3 weeks or after a month, the two images can be compared with each other, using which we are able to understand what is the change in the wavelength due to the deformation of the land subsurface. During the first pass, land was here. During the second pass of the satellite, the land has moved downwards. So, we are able to understand the changes in the surface of the earth based on the change in the wavelength. So, with the help of this, we are able to today map the changes in the land surface at a centimeter resolution. Right. What are all the broad applications of this synthetic aperture radar? In engineering, it is extensively used to monitor the structural integrity of the major infrastructure in large cities. How we are able to monitor the land subsidence, right, using synthetic aperture radar, right. However, in a real urban cluster, it is little bit difficult. That also we should bear in mind. But when the urban intensity of urbanization is not very high, synthetic aperture radar help us to understand how the land is vertically subsiding, what is its relation to the structural stability of the buildings can be assessed, and we can also monitor the infrastructure, right, how urban development takes place using the aperture radar, right, because previously we would have received the signals from the ground surface. Now today we may be receiving the signals from the terrace of the buildings, right. Buildings may be 15 meter tall or 500 meter tall. So, we are able to understand how we are urbanizing using the synthetic aperture radar too, and very much it is useful in understanding the landslides, right, land creep, right. How was the land surface and how is the land surface after a landslide? We can precisely come out with an assessment of the quantum of material that got slided, and continuous monitoring of the land surface, we will be able to identify landslide prone areas. How? So, every month we are identifying or assessing the elevation of the surface. As the elevation of the surface changes, especially along the hill slopes, we can use this data as one of the layer apart from the intensity of weathering, slope angle, land use. This also help us to know how quickly the land is getting deformed to come out with a map of landslide prone areas. Also, since the radar waves can also help us to monitor water level, right, in reservoirs, this can also help us to assess the water resources indirectly. Also, it can be used to understand soil moisture and accumulation of snow and ice. In environment, we can monitor land cover changes, right, especially whether there is afforestation or there is any reduction in the forest cover or ecosystem. Land cover changes, natural habitats changes can be assessed using synthetic aperture radar images, right. How the stem size can also be assessed, right. What is the health of the forest cover can be assessed. There is a tremendous application in the field of geological as well as in disaster management. Monitoring earthquakes, right, tectonic deformation, whether a particular plate is moving downwards with respect to the other, right. We can also study the after effects of earthquakes, because here the earthquake would have resulted into change in the land surface, which can be picked up by an image, right, or an interferogram between the data collected before and after the event, immediately before and immediately after. And we can similarly we can detect the volcanoes, we can detect and monitor the volcanic eruptions. As I had told you previously, under engineering application we can monitor landslides. These are all the applications of synthetic aperture radar. I put up one case study, right, in which in Kolkata city, how synthetic aperture radar was used to understand the minor land subsidence in Kolkata city, for which this person has used NVSAT sensors of different times, right, and these are all the data of acquisition of the SAR data, using which interferograms were prepared to understand the land subsidence in some parts of Kolkata city in India. So, these are all the applications of synthetic aperture radar. As I had told you previously, it is not a proper geophysical method. Since we discussed about ground penetrating radar, I thought you should also be aware of the technique of satellite based radar system to understand the deformation on the land surface. Thank you very much.